Hello everybody, Chapter 7, Securing Site-to-Site Connectivity. Alright, we're going to talk about VPNs, what they are, that kind of thing. And then we're going to talk about GRE tunnels. Then we're going to talk about IPsec, which is sometimes used with GRE tunnels to encrypt the data because GRE itself is non-secure. Then we're going to talk about different remote access techniques. Alright, then the objectives. Again, just hit pause if you want to read those. Alright, so obviously security is a concern anytime we're using the public internet, and nowadays, because of the way bandwidth is available, we're using the internet more and more for business to connect offices. You know, back in the day, internet prices were very expensive, and we were just buying T1s, and well, T1 was 1.5 megabits. You know, I mean, what business doesn't have at least 10 megs download speed now? And obviously you can buy as much as you want. You know, I've got a group, a radiologist group that has fiber to the hospitals, to their private reading room, to 5 local hospitals, and they have 20 gigs on each fiber strand. So it's pretty nice. But again, you can buy as much as you want. So there's a lot more people using this public internet. And even though they have like private fiber run, it still runs through the central office of Time Warner Cable. So depending on your business, you have to decide, you know, is that going to be secure enough for me? For most businesses it is. You know, whether it's going through AT&T central offices or Time Warner Cable central offices, you're pretty secure. But if you're a bank and all your banking information is routing through a central office at Time Warner Cable, you don't want to take the chance that somebody there is going to be bad and start grabbing packets and making transfers and doing weird stuff. So even for private fiber or T1 lines, you would want to incorporate some kind of security. So again, we typically use VPNs across the internet. Now remember, VPN is virtual private network, and all it is we encrypt the data. You know, we wrap the data in gift wrapping so that if people see it or grab it, they can't see what's inside the packet. So hopefully our wrapping is strong enough that they can't break it. Alright, so VPNs, you know, introduced to create end-to-end private network connections. A lot of times we use these, you know, we have a headquarters office, and then we're going to go 6 miles down the road to a small satellite office with 6 employees. You know, we'll just put a small, like an ASA or a Soho box down there, and we'll create a tunnel between our router and their router or their firewall, and we'll just encrypt everything. We'll just go across the internet, and most things work pretty well that way. You know, as far as getting internet or email, stuff like that. Because remember, these things are expensive. You know, an email server, a file server, getting business internet. So it's easier for the small branch offices to just piggyback through to the head office and then get information that way, or get their files and their email and stuff, rather than putting servers out at every office. And you can create VPNs with a lot of different hardware. You can do it with routers, you can do it with firewalls, although Cisco's firewalls are ASAs, adaptive security appliances. But a lot of different stuff. A lot of, well, I don't say a lot, but you know, I occasionally do see people with a router at their perimeter instead of a firewall. Personally, I'm not a fan of that, but you know, to each their own. Alright, the benefits of VPNs, obviously cost savings. You know, I'll just use my regular internet that I already have instead of buying a T1. You know, T1s are expensive. 6 miles down the road, several $100s a month, and you can assign like 3- and 5-year contracts for those things. They're terrible. VPNs are also scalable. You know, I can pop in as many as I want. If my firewall only supports 10, I can go buy a license pack and get more added on. So I don't necessarily have to buy hardware. And most of your firewalls, you know, support so many, and then you can add more later, you know, with these security packs or licenses. So then you can add people working from home, you can add branch offices, however you want to do it. Alright, they're also compatible with broadband technology. You know, whether you got DSL or cable, you know, whatever you're running at home, VPNs will work that way. I mean, they even work with dial-up. Alright, and then again, as far as security goes, you can get some really good encryption with VPNs, depending on which ones you buy. 160-bit encryption is tough to break. I mean, unless you piss off China, your average person is not going to break your encryption. Alright, so we have site-to-site VPNs, and this is typically what you see in the workplace. And what happens is you create a VPN between your firewall at your business and the firewall at another business. Let's say it's a satellite office. So you only encrypt traffic from firewall to firewall or just across the internet. And then behind those firewalls on the corporate networks, there is no VPN. Everybody runs normally. So that's a site-to-site VPN. So these are nice when you can do them because your internal traffic isn't all bottled down by encrypting packets and decrypting packets. Your internal network can do whatever they want, and packets are not encrypted. But when they hit the firewall to go out to that other destination, then they're encrypted. And remember, when we create these VPN tunnels and we pass data across there, we're adding a lot of extra overhead. I got to gift wrap that packet with encryption, then I send it, and then when you get it, you have to ungift wrap it. So think about Christmas morning, how long it takes you to unwrap your presents. It's kind of the same overhead. So again, I've got my firewall at my corporate office, and it hits your firewall at your corporate office, and then back here with the client, you have no knowledge, like there's no VPN software installed. Everything is normal on your network. So that's a site-to-site VPN. Alright, the other type of VPN is a remote access VPN. And this is typically where you have your tele users working. Basically, you go to their house and you install software on their PC. And you've got the Cisco AnyConnect Secure Mobility Client. Yay! Anyway, so now anytime that user wants to do some work and connect to the office, they have to run their VPN software. Now, this is a problem. We used to use this pretty heavily in the old days, but it became a problem because everybody has different PCs. Hey, what if I have a Mac? What if I have a PC? Hey, what if I'm running Windows 7? What if I'm running Windows XP? What if I'm running Windows 8? Now 10's already out. So a lot of stuff. And then what kind of antivirus are you using? So it creates a lot of problems. Plus, these VPN clients are sometimes kind of hard to install. They ask a lot of questions. What kind of encryption do you want? What kind of authentication do you want? Let's put the keys in, stuff like that. And there's a lot of users that just were not able to do this on their own, even with detailed directions. They always had problems, or their security software on their PC would kick off and say, hey, and then you would have to go out to their house. Well, the last thing you want is your corporate IT guys visiting everybody at home and screwing around on their PCs and that kind of stuff. So a better option is what we call SSLs, and we'll talk about those a little bit later. So with the remote access, again, you're encrypted from the PC all the way to wherever your terminating device is, which is typically the headquarter firewall. And then after that, your stuff goes unencrypted. Alright, so now we know about the VPNs. We know we can have a site-to-site or we can have remote access. We know site-to-site is just a point-to-point, firewall to firewall, and we know remote access is from the user all the way to the corporate headquarters. So now we'll talk about GRE tunnels. You can actually create tunnels with a Cisco router. So GRE tunnels are something that Cisco introduced. They're basic, non-secure, site-to-site VPN tunneling between router and router that Cisco did. So Cisco created this because there are other encryption software packages or devices out there, like IPsec. So you can create this tunnel between the two routers. So now I don't necessarily need a firewall. Let's say I'm a bank and I got a remote office down the road. I can go from my router to their router on a point-to-point, a T1 or a T3 or fiber or whatever it is, and I can create a GRE tunnel, and then I can just do IPsec across the GRE tunnel, and I didn't have to buy any extra hardware. I didn't have to buy a firewall. I didn't have to change my design, things like that. So a GRE tunnel is just a generic routing encapsulation, a very basic non-secure tunnel that you can do between routers or Cisco devices. Alright, they're relatively easy to configure. Again, obviously it adds more stuff to the header. Now remember, again, in these pictures, we always see the data like this, and we see all this information. So it looks like the header is actually bigger than the data. But remember, the header size is typically measured in bytes. I'm sorry, bits. So 24 bits, 32 bits as the header. But the data is actually measured in bytes. So remember, the entire packet size can be like 1,500 bytes. So kind of keep that in mind when you look at these slides. All right, so GRE is defined as an IETF standard. IP Protocol 47 is used. What the heck does that mean? GRE encapsulation uses a protocol type field to the header, blah, blah, blah. So it's stateless, doesn't have any kind of flow control mechanisms, no strong security. So that's really the big thing that you have to remember. A GRE tunnel is just a basic generic tunnel between two routers. And then you have to add your own security mechanism. So not a ton of uses for it, but again, you still have people out there that are very Cisco oriented, and they actually have like a router at their perimeter that goes to the internet, and they do all their security settings on the router. So when they want to create VPN tunnels to remote offices, they have to use GRE tunnels or some other method. And then again, we talked about even if you have a point-to-point that goes through a central office, you still might want to have that secure. So GRE tunnel is kind of the way to go. So again, it's got its uses. All right, so configuration. So we do interface tunnel 0. So we name our tunnels. So we're going to call this tunnel 0. And then we do tunnel mode GRE IP, because we're going to be using IP. And then IP address, we give it the tunnel address, and then we give it a source, and then a destination. So a little bit confusing, because you're like, well, if my interface is 209.165.201.100, so if this is my interface, what the heck is this number? You actually have to give the two ends of the tunnel its own IP address, which gets kind of confusing. So we give our end of the tunnel an IP address, 2.1, and then we say, hey, the source traffic is going to come from my exit interface here at 201.1, and its destination, it wants to go to here to 201.2. And then again, you can turn on OSPF and turn that stuff on, but that's not necessarily required. You only need to do 1, 2, 3, 4, 5 commands to make your GRE tunnel. But then you have to go to the other end, and you have to do the same thing for him. So he goes, interface tunnel 0, tunnel mode GRE IP, and then he has to assign his tunnel an IP address, and then he creates the source and destination. And then at that point, your GRE tunnel is done. So only 5 commands to make it happen. It just gets confusing because you have to give the tunnel an IP address, which is really kind of weird. I don't know the process behind that, why it couldn't just use the source destination IP address, but I digress. So this is a good one to have in your notes. Have a page that says GRE, and then have these 2 configurations written down, and make sure you write down, hey, this IP address here is a made-up IP address that I give my GRE tunnel. So again, that's also another reason why we create so many .30s or /30s when we're IPing our network, because you never know how many of these 2 IP networks you're going to need, how many router-to-router connections. And you'd be surprised over a 10-year period how many different routers you'll add, and like, crap, I got to add another one, I got to add another one, I got to add another one. And each router may add 1 or 2 or more of these /30 networks. Alright, and as with anything that we configure, you always need to verify to make sure it works. So how to verify: show IP interface brief, include tunnel, and you'll see that your tunnel will show up. So your tunnel shows up just like an interface does. Or you can do show interface tunnel 0, and that'll give you your tunnel information. Or show IP OSPF neighbor, and they'll show you that, hey, you're connected to that guy through tunnel interface 10. So a lot of different ways. Alright, so now that you've created the GRE tunnel, we need to encrypt it. So we're going to talk about using IPsec, and IPsec just stands for IP security. And typically when we think about IPsec, we think about encrypting our internal networks. Most banks run IPsec or some other device internally, where most companies don't really do internal security like this. Because now every PC is going to encrypt data going to even his neighbor PC that sits right beside him. So with IPsec, we can create IPsec VPN. So we can go from business to business. We can go from the mobile worker to the business, however we want to do it. IPsec is pretty flexible. It's built into IP6, so if you're already running IP6, it helps a lot because, again, it cuts down the overhead. Alright, information on IP6. So IP6 functions defines how a VPN can be configured in a secure manner. Woo! It's a framework of open standards. Now, it's not bound to any specific encryption. You've got a lot of options. You have options on encryption. You have options on authentication, keying your stuff, however you want to do it. So IPsec kind of does all that stuff. Alright, and then all implementations of IPsec have a plain text layer 3 header. So routing is not a problem. Remember, the header for routing purposes is not going to be encrypted, so nothing special has to go on the routers theoretically, unless you want to encrypt it all the way through. And it supports all kinds of older layer 2 protocols like ATM, frame relay, things like that. All right, characteristics, open standards. Algorithm independent, so it can use a bunch of different ones, Diffie-Hellman, whatever it wants to use. IPsec provides confidentiality, integrity, and authentication, which is CIA. So when you see CIA, as far as we're talking about security, they're talking about confidentiality, integrity, and authentication. And then it acts at the network layer, protecting and authenticating the IP packet. So again, they're talking about confidentiality, integrity, authentication, and then anti-replay, so CIA. So we know in order to keep something confidential, we don't want somebody to look at that, so we do encryption. Integrity means that the data has not been changed or tampered with, and authentication is I have proved I am who I say I am. So make sure you know the difference between those. And then anti-replay is just to detect and reject replayed packets, so that you know if somebody's spoofing your packets. Like we talked about a man-in-the-middle attack a while ago. If somebody tells the router that they're you and they tell you that they're router, they actually receive your packet and then resend it out. So this would stop that. Alright, then some basics. For encryption to work, both the sender and the receiver must know the rules. And the rules are based on algorithms. Excuse me. Sorry, the rules are based on algorithms or associated keys. So in this case, Gail uses her key, and she's going to take this transaction, pay to Jeremy $100, and she's going to encrypt it. And it looks like this, big gobbledygook. So that's what we call that. We call that hashing. When we change the plain text into a bunch of gobbledygook, we hash it. And then when it goes across the internet and it gets to Jeremy, it still looks like that. So if somebody were to intercept those packets and make a copy of them, he theoretically wouldn't be able to read anything out of this. He would have to have your key to decrypt this correctly. Now remember, any encryption is possible to break. It's just a matter of how much time and money you want to put into it. For some reason, if you, let's say, make China mad, China will find a way to break your encryption. They'll have 100,000 people spending billions of dollars to crack your stuff. So don't make China mad. But your average everyday cracker, the high school kid that found some cracks on YouTube and things like that, will not be able to crack it if it's strong enough. All right. So as far as the algorithms go, we have two main types. We have symmetric encryption, and then we have asymmetric encryption. Now, symmetric encryption is typically easier to break, but it's also easier to implement. And then asymmetric encryption is a little bit harder. So with symmetric encryption, the same key is used on both ends. So it's kind of like, I guess a good example would be WEP. If you ever set up WEP on your laptop for wireless security, you have to go to the access point and you put in your password, Sparky123. Then you have to go to the laptop and type in Sparky123. So then they're both using the same set of keys. And some examples of that are DES, triple DES, which is no longer considered secure, and then AES, and AES is the stronger one. So when they say triple DES is no longer secure, remember DES was first and then they came out with triple DES. Now triple DES wraps the packet 3 times in DES. So it's like doing DES 3 times on the same packet. So imagine gift wrapping something 3 times. But when they say no longer secure, it means it was broken maybe by a criminal organization or something like that. So if you're a bank, that would no longer be considered secure for you. For an average user, you're at a manufacturing plant and you're making tires. 3DES is probably okay. I mean, unless you've got a special rubber patent like Goodyear, that kind of stuff. Alright, asymmetric key uses two different keys. So knowing one of the keys doesn't allow the hacker to deduce the second key. So one key encrypts the message while the second key decrypts the message. And then typically here we have public key authentication. And another example is RSA. But let's talk about public key authentication. Let's talk about the Diffie-Hellman for a second. Alright, Diffie-Hellman is not an encryption standard itself, but it's a way to exchange keys and create these two separate keys. So let me give an example of the Diffie-Hellman. Alright, I don't know if I blew this up so the writing's kind of funky. But here's an example of Diffie-Hellman. Now you have to agree on some constants before you do the exchange. So basically, like when I create the domain or when I join the domain, or that kind of stuff, we can create these constants. And the constants are: I need a prime number and I need a generator. So both of us can have a prime number and a generator. So in this example, Alice chooses a secret random number, so her PC generates lowercase a, which is 6. And then Bob, his PC, chooses lowercase b, which is 5. So they both choose a random secret number. And then they both use that number in this algorithm, which is the generator times the a mod p. And she ends up with her formula. When she puts her 6 into that formula, she generates a 9. And when he puts his 5 in the formula, he generates a 5. So now she has a 9 and he has a 5. So she sends the 9 to Bob and Bob sends his 5 to her. Well, then she puts Bob's 5 in her thing and she generates an 8. And Bob puts her 9 in his formula and he generates an 8. So now they have a secret key from the private keys that they generate. Like, they both send each other 9 and 5. So if somebody were to grab your 9 or your 5, they would still not be able to get the actual key that you used on that, if that makes sense. They would also have to have this formula and have to have all this information. They would have to know the prime number of the generator. But you already created that when you joined the domain, a year ago or something like that. So that's how we can have public keys, 9 and 5, and people can look at the public keys and gain access to them, but without the rest of the numbers, they'll never be able to generate the private key. So that's how these keys can go across the internet, and you don't have to worry about somebody grabbing them unless they obviously have all this other information in here. But then using the Diffie-Hellman Key Exchange, we can then generate a secret key that nobody would know, and then we can use the secret key together to encrypt our information back and forth. And somebody gaining access to the public key would not interfere with that. So the Diffie-Hellman is the best way to explain private key authentication. Because when you first read about it, oh, I generate a key and you generate a key and we swap keys, and then it doesn't matter if somebody grabs our keys because it doesn't work. It's like, you're like, what? So I hope that kind of clears that up for you. So that's how PKI or IKE, public key authentication, works. We agree on some stuff beforehand. Typically it's early on, or when Diffie-Hellman is when your encryption standard is installed on the PCs. Depending on what package you're doing. If I'm doing one, as I'm installing the encryption package on your PC, I may have to pick the prime number in the generator. And then when I go to Bob's PC, I got to do the same thing. So that's how the prime number and the generator can be the same. Alright, so remember, the Diffie-Hellman is not encryption. It's just a way to exchange keys and have public key authentication. Alright, it is part of the IPsec standard. It allows all kinds of encryption methods, AES, MD5, SHI, hashing, so whatever. Now, remember, there's a difference between these three, DES, 3DES, and AES, and then MD5 and SHA. These three are encryption standards. They will encrypt your data. These are hashing programs to hash it, to change the way things look. So Again, using the Diffie-Hellman, we both have public keys, and eventually it turns into a secret key between us, and then we can use that to encrypt and decrypt the data, and if somebody gets our public key, it doesn't matter. Alright, as far as integrity goes, that's why we hash these algorithms. So by hashing it, I can say, hey, and I can hash by different standards. You know, what if I take the timestamp when you hashed it, and then I use that number as part of my hashing algorithm? And then when you get the packet, if it was hashed, you know, not long ago or something like that, somebody hashed it. Like, so let's say somebody. So I hash my packet. Well, I'm really screwing this up. So I hash my packet and I send it, and somebody grabs it, and then they de-encrypt it for a day or two, and then they re-encrypt it and send it back. Well, when the receiver gets it, he's going to like, hey, this timestamp doesn't match. It's not even close to, you know, there's no way you sent this 3 days ago, and I just got it. So he would know that the integrity of the packet was suspect. So there's other methods where, like in this case here that they're talking about, I can hash it and then send it, and then when you receive it, you produce another hash from my hash, and then you compare the two hashes, and then if they're the same, it works. So what I'm saying is, when I send this $100 to Jeremy, I'm using this hash, and then it goes across the internet, and then when you get it, you create a new hash based on my hash, and if your hash and my hash both work and you can read them, then you know something worked. Or in this case here in the slide, they're showing, hey, if I hash it like this and send it across the internet, and somebody intercepts it and changes it, it's going to show up different. So hey, you know, I sent you 100, but you modified it to be $1,000. So I know the hash is incorrect. So that's integrity, you know, checking the hash. And there's a lot of different ways, and you really have to dig into the security class and the security books to dig into this hashing techniques. You know, for me, all I know is hashing is turning a regular plain text into a bunch of gobbledygook. And obviously the stronger the hash, the more bits it is, the more secure it's going to be. Alright, don't get too much into this hashing stuff. It's not a big factor on the exam. You know, the exam's going to talk about how to do GRE tunnels and turn on IPsec or something like that. It's not going to get into all this integrity hashing stuff. This is just more of some extra information so you understand how the security stuff works. Alright, so as far as hashing goes, we have two standards. We have MD5, which almost everything supports nowadays. That's like 128-bit. And then we have SHA, and SHA can go up to 160-bit. So obviously SHA would be a lot stronger. But remember, the stronger your encryption, the longer it takes to generate those keys, and then the longer it takes to decrypt those keys when they get to the other end. So it all depends on what you're doing and how secure it has to be. Remember, if you're at a factory and you're just making widgets and nobody's interested in your widgets and you're not doing any financial data across your lines, you know, MD5 might be perfectly fine with you. Actually, you might even be fine with plain text. Alright, and then they talk about authentication. Remember, authentication is I am who I say I am. You know, I'm trying to prove who I am. And typically we do this with like username and passwords. But across the internet, it could be easy for somebody to grab that information. So we've got two other options. We have PSK, and then we have RSA. Now, RSA is crazy secure, and we'll talk about that in just a second. But PSK is a secret key is shared between the two parties using a secure channel before it needs to be used. So now we're talking about symmetric key. I put in my special VPN password, and you already have your special VPN password configured, and that kind of creates a tunnel. So it's kind of like WEP. WEP would be a good example of that. Now, obviously, this would be a little bit stronger than WEP. You know, remember, I'm using WEP as an example of how to configure it, but it's not as weak as WEP. All right, and then we have RSA. RSA is crazy. If you've ever seen the RSA keys, basically imagine if you play World of Warcraft or you play any of these video games and you have a secure key authenticator that generates those new random numbers. That's RSA. It used to be only used in like finance and healthcare, but nowadays it's used all over the place. Most of the big MMOs support it, and they sell their keys, things like that. But basically what it does is it randomly generates new numbers for each user, and it can be as many or as often as every 1 minute. We had keys for our nurses at one place where I worked, where each nurse had their little key fob on their keychain, and it would generate a new number every 60 seconds. And when they would authenticate and they would try to dial in using the VPN, they would have to type in their username and that number. And that number, again, it changes every 60 seconds. So they had like little bars on there that they could see, if I had 6 bars and the key was good for 60 seconds, so I had time. If I only had 2 bars left, it's only 20 seconds, the nurse would have to wait until a fresh key was generated and then type her stuff in and then hit OK. Because by the time you type it all in, you hit enter, and then it encrypts all your stuff, goes back to the headquarters and checks the time. If you only had 10 seconds left, you might not make it. Plus some of these nurses type slow. So that's kind of RSA. So the RSA tokens nowadays come in all shapes and sizes. We had these big nasty key fobs, but again, they come in all kinds of shapes and sizes. You can get them in, for your video games, you can get them as credit card size, so they fit in your wallet, things like that. But here you can see the little tick marks. So this one has 30 seconds left on this key, and then a new key is generated. So they're kind of a pain to set up. Like as an administrator, each key has to be synchronized to the server, and then you can hand it out to a user. And then sometimes they may become unsynchronized, and I don't know if it's just something that happens over time or if they drop it or something like that. But we would occasionally have nurses come in and say, hey, I can't authenticate, and then we would resynchronize their key, and then it would be fine. So a little bit over it, but crazy secure, because again, you're generating a new key every 60 seconds. How cool is that? Alright, and then when you're using IPsec, you got 2 flavors. You have the authentication header, and then you have the encapsulating security payload. Now, the authentication header doesn't provide any encryption of the packets. So I'm kind of confused on that. It provides authentication only on the header information, whereas the encapsulating security payload will then encapsulate the packet. So in this case, again, with the authentication header, all data is in plain text, and this is just providing authentication security. So if somebody doesn't authenticate, then they don't get the data. Then you don't continue sending. Where down here, everything is covered. So now we have encryption, authentication, and integrity. So I guess you got to kind of choose which one you want to go with. How secure does your stuff need to be? Remember, the stronger your security is, the less usability, the more overhead, the slower the stuff happens. Now, when I say slower, you may not notice it with the human eye, but again, we can benchmark that. And if we take all these different things that we're talking about, like authentication, broadcast, and things, and we eliminate all this stuff, we would see a noticeable improvement in speed in our network. All right, to kind of bring this all together, you have 4 basic building blocks of IPsec. You have the IPsec Framework Protocol, which is a combination of ESP and AH. Remember, ESP is the encapsulation, encapsulating security payload, and then AH is the authentication header. And then you have to build in confidentiality, so either DES, 3DES, or AES. And remember, AES is the strongest. And then for integrity, we need MD5 or SHA. And then for authentication, PSK or RSA. So I need to make sure that somebody can't see my data, so I need to use AES. I need to make sure that nobody messes with the data in transit and then tries to resend it to me, so that's where MD5 and SHA comes into play. Then I need to make sure that I only pass this stuff to whoever's allowed to see it, so that's where RSA kind of comes in. So I hope that kind of clears it up for you. So IPsec has a lot of different blocks in there. Diffie-Hellman to do public keys, authentication to prove somebody is who they say they are, integrity, has somebody changed my packet or has it been damaged or modified, confidentiality, if somebody does grab a packet, can they break it and see it, and then different choices for my headers. So a lot of different pieces go into IPsec. Now, the slides or the book don't really get into how to turn on IPsec in your GRE tunnel, but I found a quick website that had the information here. So after you create the tunnel, so here, they create the tunnel, I create tunnel 0, I give it an IP address, and they do some other stuff. This is their example. I don't know if you can see this. Let me see if I can make this bigger for you. Hold on. Alright, here's the best I could do on short notice. So, and again, this is how complicated this is. Obviously, it's not a CCNA topic. That's why they do not cover it in the slides and stuff. So, first step we need to do on R1 is we need to create the policy, so crypto ISA KMP policy 1. Then we need to set the encryption, the hash, the authentication. We give it a group and how long it's going to go. And then they give you some information. Hey, this is the encryption, blah, 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 blah. Then we need to define a pre-shared key. So crypto key, blah, and then there's the key, firewall CX, address, blah. So the pre-shared key is that. Now we need to transform the set used to protect our data. We name this TS, blah, 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 blah. Mode transport. Remember, you have tunnel and transport mode. Tunnel mode is typically used between two endpoints, and transport mode is for like end-to-end security. And then some more stuff, and then that's it. So all this stuff from here up is all the stuff that has to be done on one router. So again, that's way out of the scope of the CCNA, but just so you know that it's there. I guess this would have been an easier one. On R2 they got it all nice and together without all the explanations. So you can see there's a lot of stuff that kind of goes into this. This is where you typically, once you get out of your CCNA program and you decide to specialize and you do CCNA security, this is where you would get into this stuff. Now, I probably just scared a bunch of you, and you're like, well, I'm never going to go CCNA security. It's not that bad. Again, it's just like anything else, like frame relay or whatever. Once you learn it, it's actually pretty easy. All right, and then finally, we're going to wrap up this chapter with remote access. So there are two primary methods for securing or deploying remote access as far as CCNA goes, and that is SSL and IPsec. So we've already kind of talked about IPsec, so let's talk about SSL a little bit. SSL is like a godsend to the IT guys. The IP guys, I'm freaking out. All right. So, give an example. At the place where I worked, we were doing remote access VPNs. So we were going out to the client's house, and we were actually installing the VPN software. And it was a nightmare. Like we had a 3.5 floppy disk that we used that had the key codes and stuff on it. And then when we went to one PC, and she didn't even have a floppy disk, we're like, oh crap! Of course, the tech didn't bring out a USB one, so then we had to go all the way back, get the stuff, go all the way back out. So it sucks up a lot of time. And then every user's different. The one, oh yeah, I got internet. Yeah, it's really fast. You go there and it's dial-up. You're like, what? Remember, dial-up is so slow that sometimes these security protocols don't have time to authenticate, and they'll time out. So SSL is awesome because it eliminates all that hassle with the users. So what we did was we purchased an SSL appliance, and I can't think of who it's from. I want to say it was from Barracuda. So there's a lot of different companies. If you type in SSL appliance, you'll find a bunch of different ones. Barracuda, WatchGuard, Cisco, SonicWall. I almost said Dell because Dell bought SonicWall, but you get the idea. So on this appliance, we were able to buy or grab another IP address from our vendor or our ISP, and get it assigned to this device. And then the device would authenticate the user back to our server. So basically, the user, all they had to do was open up a web browser and type in our address, and then we got a name for it, so our domain name. So they just open up their thing and just type in this name, and then it would go to our SSL appliance through their web browser, and then it would come up with an authentication page, and it was SSL, so it's wrapped into encryption, and they could put in their username and password, and then the appliance would then go to our domain controllers and authenticate them, and if they authenticated, then it would give that user their home page, and their home page would then give them access to whatever they had, email, files, programs that they had access to. So again, it was kind of a pain to set up at first because we had to make a couple different settings. Hey, this is what the nurses are going to see on their home pages. This is what so-and-so is going to see, and we had to set all the users up. But once it was done, woo, it was awesome! Now no longer do we have to give these people, 12 pages of instructions of how to install the software. No longer do we have to go out to houses and check this stuff. No longer do we have to care what they had on their PC, that kind of stuff. They use their PC. They could use any PC they wanted, Mac, iPC, whatever. Get to the internet and then open up a web browser, any web browser, because most of them were supported, and then just type in this address, and it took them right there. It was all secure. It was awesome. So Cisco comes with this AnyConnect secure mobility client software that you could use if you want to do a client, but you can also do clientless on the ASA 5505. And I think you get introduced to that in CCNA security, but in our firewall class, we have you guys do that. We have you first connect using the software, just to show you what a pain in the butt it is, and then we have you use the SSL to just connect using the browser, and you're like, holy crap, why didn't we do this first? It's like, well, because then you don't understand the pain of having a client to install. So again, Cisco has AnyConnect Secure Mobility Client with SSL, and then they have client lists. What you want at nowadays is client lists, because you never know what somebody's going to have at their house. You would be surprised some of the PCs that people are running. You know, there are people that are still running Windows XP, which is an awesome system, but there's no way that that's going to be secure now that Microsoft has quit supporting it, and new vulnerabilities are happening every day. So again, the choice is yours, and with Cisco, again, you got both of these options. They both come standard with an ASA 5505. So you could do the client, or you could do the SSL clientless. Again, 9 times out of 10, I recommend the clientless stuff. So again, you know, the easy VPN software creates the tunnel, goes across the internet. Your stuff is encrypted, so you're relatively safe. So again, it all depends on what you're doing. You know, I don't exactly know what the standard is for financial offices. They may have to have something even more secure than SSL. But for the rest of us, SSL is the way to go. Alright, so Cisco's Easy VPN solution, and again, it is freaking easy, has a server, a remote, and a client, and again, you don't even have to have the client stuff, which is kind of nice. So it's flexible, it's scalable. Again, you can always buy like a security pack to increase the licenses. Like I think your ASA by default comes with a 10 access license or 5, something crazy small. And then you pay a couple $100, and you put in the security license, and then you all of a sudden